During today's podcast, we're going to be learning about polynomial functions and their graphs. So some of the learning targets for today, we're going to identify the equations of polynomial functions. We are going to recognize characteristics of graphs of polynomial functions. We'll understand the relationship between degree and turning points, determine end behavior of functions, use factoring to find zeros of polynomial functions, identify zeros and their multiplicities, and then use these things. Use all this to be able to graph the polynomial function. Just sketch a rough graph of it. All right, so starting out with definition of polynomial. So polynomial is a algebraic expression involving variables and their coefficients, where it's a series of addition and subtracted terms. Remember, polynomial means multi-term monomial. So this just means more than two, or really more than one for poly. And the monomial part of it is indicating how many terms there are. One of the key takeaways, exponents must be a whole number. They can't be fractional, and they can't be negative. So answering questions about whether or not certain things are polynomials. Well, due to this fact that this is negative, this is not a polynomial. Due to the fact that this is negative and this is fractional, not a whole number, then this one's no. So those are an example of one that would be a polynomial. Might be something like negative 3x cubed plus 2x minus 4. Notice how all of the exponents are positive and whole numbers. Okay, so it's important that we have an understanding of basic polynomial graphs as we know, really as we think about these and analyze polynomials. So it's important to remember what x squared looks like. Remember, x squared, it's a parabola. It's a parabola. It's that U-looking graph. X cubed is a cubic function, and it's kind of like a parabola, but it's where like the left side of it got flipped down below the axis. So that's the general shape of an x cubed function. Other polynomials, essentially, their domain is all real numbers, so it goes forever to the left and right along the x-axis, and they're smooth, continuous, with rounded edges. So when it changes directions, it doesn't do so sharply, it'll do so in a curved fashion. So this might be an example of a quartic polynomial, like a fourth degree polynomial, meaning the highest exponent would be 4. So notice how it goes forever to the left and right, and it's smooth when it changes directions. Okay, so what we're trying to do here at the end of the day is we're trying to put together information that allows us to draw a rough sketch of the graph of polynomial. Now, I call it rough because it's not every point is going to be exactly in the correct spot, but we're going to use certain characteristics of these polynomials to create that rough sketch. So the number of turns indicates how many times it turns around and changes from increasing to decreasing. So for this one in particular, that would be 1, 2, 3 times it changes direction. That's what I mean by 3 turns. This one would have 1 turn because it changes direction 1 time. This one would have 0 turns. It does not change direction at all. End behavior, that essentially what does the graph look like on the edges? What does the graph look like on the edges? We'll go more in detail with each of these. I'm just providing an overview of what we're doing here. What does the graph look like on the edges? And then x-intercepts and zeros. You might remember what x-intercepts are. 0 is a synonym for x-intercept. Root is another synonym for these things. And x-intercepts describe where and how does the graph interact with the x-axis. So we'll answer these questions and we'll use these and put them all together at the end. All right, so Number of turns. So how do we determine how many turns a polynomial will have? Well, it's all about the degree of that polynomial. Remember, the degree represents the highest exponent. Highest exponent. So the number of turns always has to be less than or equal to whatever one less than the degree is. Whatever one less than the degree is. So for our sketching purposes, we're going to make the number of turns equal to the degree minus 1. But in reality, it could be less than or equal to degree minus 1. But for us, degree minus 1 is what we're going to use for number of turns and how we sketch our graph. So the degree for this one is 3, which means number of turns would be 2. So 2 turns. So an example of a 2-turn polynomial would be 1, 2. Could be this polynomial. We don't know anything else about it, so this is just an example of a 2-turn polynomial. This one, the degree is 2, so that would mean there'd be 2 minus 1, which is 1 turn. 1 turn just means, all right, we start out going either up or down and turn around once. So it'd be a parabola, which makes sense, but we basically know about quadratic polynomials. They always form parabolas. And then a 4th degree would have 3 turns. So if we started going this way, 1, 2, 3. And there's an example of a 3-turn, or a polynomial with 3 turns. So it's pretty simple. Basically, the number of turns equals whatever the degree is minus 1. Okay, end behavior. End behavior. So end behavior answers the question, what is happening to the function as x approaches infinity and as x approaches negative infinity? It's 2 different questions. You're going to be basically what's happening as our function goes to the left and as it goes to the right. What's it doing? Is it going up to infinity or is it going down to negative infinity is the question we're going to be asking. And it's determined by 2 characteristics of the polynomial. So is its degree even or odd? So the degree, whether it's even or odd, and what the sign of that coefficient of that highest degree term is, and whether it's positive or negative. So what do I mean by highest degree term? So this polynomial here has 3 terms, and the highest degree term of those 3 is this one, because the x is raised to the highest power among those 3. So that's why we're looking at this. So for this particular one, our degree is even. Our degree is even. Our leading coefficient, where we're trying to decide if it's positive or negative, and the sign is positive. The degree for this particular function, the highest degree term, so of these 3 terms, the highest degree term is this first one. So that's what the term we're going to analyze when it comes to degree and sign of the coefficient. So our degree here is 2 because this exponent is 2. So our degree is even. It came from the fact that it was 2. Leading coefficient is positive leading coefficient. So whenever the degree is even and the leading coefficient is positive, the end behavior is going to match the end behavior of another common even degreed positive leading coefficient. That would be same as x squared. Remember, x squared looks like this. It's a parabola. So that means the end behavior is going to go up to the right and up to the left. And the way we describe that in simple terms is we say rises right and rises left. So that's the end behavior. And that's the graphical depiction of that end behavior. Remember, our graph might do some weird stuff in the middle depending on what else is going on. But the end behavior is still going to be rises left, rises right. Okay, second problem. So we look at our highest degree term among these 3. It's this first one again. our degree is even, which is 2. Leading coefficient this time is negative. Notice that's different than this one. And the end behavior, it's going to look like, rather than positive x squared, it's going to match the end behavior of negative x squared. If you guys remember from our transformation unit, all a negative out front does is flip our parabola upside down. So it'll instead look like this. It'll match the end behavior of this function. So we know it's going to go down to the left and down to the right. And the way we say that, instead of saying rises each way, it's going to be falls right and falls left. And that's how we can describe the end behavior. And when we go to graph it, it's going to look like that. All right, I've got two more possibilities for what the end behavior could be. So we haven't dealt with any odd degrees. So notice how our highest degree term here now is odd. So we have an odd degree from the fact that this was 3. We have a positive leading coefficient, this one's positive again. So odd and positive, if you can think of back to an odd positive function, x cubed, odd with a positive leading coefficient. So we know it's going to have the same end behavior as x cubed, which remember x cubed looks like this. So it's going to go down on the left side, up on the right side. And the way we describe that is by saying falls left and rises right. Falls left, rises right. Okay, for this last example, notice we have an odd, so of our 3 terms, we're looking at our highest degree term here. It has an odd exponent, so its degree is odd. Leading coefficient now is negative rather than positive. So our end behavior is going to be the reverse of positive x cubed. It'll be like negative x cubed. So it'll switch the other way. It'll look like that at the edges. So it's going to go up as we go to the left, down as we go to the right. And remember, it could do some different stuff. It's not going to look exactly like this, depending on what the x-intercepts are and all that fun stuff. And we'll get to that in a minute. So, and the way we describe this with words would be rises left and falls right, as far as the end behavior is concerned. Okay, so take-home message, end behavior, it's unaffected by how many times the polynomial graph turns or by the x-intercepts. It answers the question, what is happening at the edges? Remember, it could turn once, twice, 3 times. It could look like this, or it could have just looked like that with the same end behavior. That's the take-home message. Okay, moving on actually, let's summarize this with a chart. So again, remember, I've organized this into a little chart for us. This would be a good thing to either take a picture of or copy into your notes. I'm going to copy these in here. And again, the logic to this is as simple as, remember, even and positive looks like x squared. So even and positive, it'll go up to the right and up to the left, just like the graph of x squared would do. If it's even and negative, that's kind of like negative x squared. So that would just be the upside down version of this. Falls to the left, falls to the right. If it's odd and positive, it matches what x cubed would do as end behavior. So x cubed, remember, looks like this. So our function that's odd and positive will go down to the left, so falls to the left and rises to the right. And then if it's negative x cubed, it just does the opposite of this. So rises to the left, falls to the right. And this is just one of the pieces of the puzzle that we're going to use to draw a rough sketch of our polynomial function. All right, last thing. Last piece of the puzzle we need. So we got to be able to analyze x-intercepts and zeros. Well, what is an x-intercept or zero? Well, and another word for it is root as well. Root, if you see the term root, that means the same thing. And they are, well, locations where the function, or where the graph, the curve, our polynomial curve, intersects the x-axis. And remember, an intersection point could both look like a crossing of the axis and also just a touching and turning around. I didn't draw that very well. But like either a cross and just like kind of like a bounce off. So that'd be an x-intercept and this would be an x-intercept. And this is an important distinction. Those are both x-intercepts. All right, how do we find it? Well, graphically speaking, if we were given a graph like I just drew here, the x-intercepts would be the x value here. So that might be 2 to the left, so that might be an x-intercept of -2. And this might be an x-intercept of +1, depending on where it crossed. But remember, it's the x value, the left and right, where it crosses the x-axis. So that's graphically, but we're going to be mostly focusing on algebraically. Algebraically, we have to use our polynomial function solving, our polynomial equation solving tools. The main ones we're going to be using are factoring and the quadratic formula. Factoring and the quadratic formula. Okay, so finding more information about the zeros. So there's something called multiplicity. If you see the term, what's built into the term multiplicity is multiple. And the multiplicity of zeros just indicates the number of zeros at each x value. So if we recall, when we're finding zeros, we set a polynomial function equal to 0. So let's say we have this right here. X squared plus 4x plus 2 is our polynomial function, not plus 2, plus 4, equals 0. And we're setting this equal, we're finding the zeros of this. Well, one way to do that would be by factoring. So we're looking for things that multiply to 4 and also add to this +4. That'd be 2 and 2. Well, x plus 2 times x plus 2. Notice, and remember our steps here, we set each of these separately equal to 0. So x plus 2 equals 0. This one's going to be the same. So it's x equals -2, x equals -2. So, and remember, I also could have written this as x plus 2 squared and gotten rid of that second term and would have gotten the same thing with just one of them. So this indicates a polynomial 0 with a multiplicity of 2 because there are 2 zeros, 1, 2. There are 2 zeros at x equals -2. So what you would say is you'd have a multiplicity. So you'd have x equals -2 with a multiplicity of 2, because there were 2 of them there. It kind of corresponds with what the exponent is from those factors. So let's change this to -2 since we just used that. So an even multiplicity at -2, what that would look like on the graph. Well, let me first tell you, and then we'll look at the graph. So what the multiplicity does, it affects how the graph interacts with the x-axis. As in, does it cross the x-axis or does it bounce off of it, like I referenced on this page right here? That's a crossing, that's a bounce off. So at each particular x-intercept. And the take-home message is that it bounces at even multiplicities and it crosses at odd multiplicities. So since this one was x equals -2 with a multiplicity of 2, this number is even, which means it would bounce at x equals 2. Sorry, x equals -2. So we'd go over here to -2, and we know it would touch right there, but if it was coming from up here, it would then bounce off. If it happened to be coming from down here, from below the axis, it would bounce off rather than cross. Okay? So for odd multiplicities, an odd multiplicity, and remember, an odd multiplicity would have come from something like this. Let's say it was, when we factored it, it was x plus 2 times x minus 3, or x plus 3 equals 0, and we would set these separately equal to 0. This would give us x equals -2, and this is x equals -3. Those are both kind of like multiplicities of 1 because there's no exponent. There's only 1 0 here. The number doesn't repeat itself. So it's a multiplicity of 1. But even though that's kind of a misnomer, you can't really say multiple. Multiple means more than 1. But when there's only 1, that's an odd multiplicity. So if we were to draw odd multiplicities at -2 and -3, well, let's count out here. So we'd have to cross the axis at both of those. So if we were coming from down here, we'd cross right there, then turn back around and cross right there. And then we might do more stuff as we go this way and more stuff as we go this way, because we don't know what else about this function. But that's the basic idea. Crosses at x-intercept with an odd multiplicity, bounces at x-intercept with an even multiplicity. All right, so let's practice finding a 0. Let's practice finding a 0. So we're going to have to use our factoring techniques to be able to do this. So we'll find zeros start off by saying this equal to 0. Because remember, x-intercepts, by definition, are where y equals 0. And this is a stand-in for y. So if we just plug in 0 for this, we get 0 equals x to the 5th minus 2x to the 4th plus x cubed. And now we solve this. So the one thing we want to do is start by factoring it out of GCF. So what's common to each of these terms is x cubed. So I can take an x cubed out of all of them. And then what's left, if there were 5 x's here, I took away 3, now I've got x squared left. There were a 2 and 4 x's, so I took away 3 x's, so it's just be a 2 and an x. And I took away 3 x's from 3 x's, but there was an implied 1 out front, so it's plus 1. And this still equals 0. Okay, so we have it's partially factored. This looks like it could be factored as well, so let's keep factoring this. So this part I'm going to factor into, let's think, what multiplies to get positive 1 but adds to negative 2? Negative 1 and negative 1. Multiply to positive 1, add to negative 2. So x minus 1 and x minus 1. And then I still got my x cubed chilling out front. Okay, so now, remember, whenever there's an x, even if it's to the 3rd power, x is kind of like writing x plus 0 to the 3rd. And then I've got my x minus 1 and my x minus 1. But there's 2 of them, so I can say x minus 1 squared. So when I'm setting these separately equal to 0 to now solve, I'm going to get for this one, well, x plus 0 equals 0. I'm just going to get x equals 0 with a multiplicity of 3 because it was to the 3rd power. So remember, that's an odd multiplicity. So we know when we go to graph it, it's going to cross at x equals 3. Sorry, at x equals 0. So we know it's going to cross at x equals 0 because it was an odd multiplicity. This 3 right here. All right, for the x minus 1, well, I set that equal to 0. Add 1, I get x equals 1. But because that was 2, there were 2 of those factors that led to that. It's a multiplicity of 2. So because this 2 is even, we know it's going to bounce. So our function, when we go to graph it, it's going to bounce at x equals 1. Remember, it's at whatever the x-intercept was, not what this is. This just determines is it even or was it odd. And then that determines whether it bounces or crosses. Okay, so that's how we find zeros. So when we would go to graph this, and we're going to put it all together in a second, but we would have a crossing at x equals 0. Dad, Brenna, I'm teaching right now. Okay, go ahead and tell me.
Can you please walk in my room?
Yep, I'll move in a minute, okay?
Okay.
So we cross at x equals 0. So we know it's going to cross there and then bounce at x equals 1 here. So if we're coming from down below, cross there, bounce there. And that's the basic idea. All right, last slide. Let's put it all together now. So we're using our information to figure out, to sketch the graph using number of turns, end behavior, and zeros. So how many turns does it have? Well, the turns, Brenna has to be quiet. How many turns does it have? Well, we know the degree is 4. So degree is 4. And 4 minus 1 would be 3 turns. We're not really, this is going to be more of a self-checking step, but 3 turns. All right, end behavior. End behavior. End behavior, we look at the highest degree term, and we look at its, the degree, is it even or odd? And what is the sign of the leading coefficient? So positive / negative for this leading coefficient. So we know we have an even degree because of the 4 right here. And this 1 means it's a positive leading coefficient. So that means even and positive means it's going to match the end behavior of x squared. If you remember what x squared is, that means it's going to rise both ways. Rise as we go to the right and rises as we go to the left. So that means when we can start putting this on the graph, we know it's going to end up going up like that and left like that and up as we go to the left. So finally, we need to do x-intercepts as well because we got to figure out what's going to happen in the middle here. So for x-intercepts, we set our polynomial equal to 0. So x to the 4th minus 4x squared equals 0. I can start by factoring out a GCF. So I've got x squared times x squared minus 4 equals 0. Remember, this is kind of like that x plus 0 squared. So we know this is going to be x equals 0 with a multiplicity of 2. Remember, that's even. So we know it's going to bounce there. Bounce at x equals 0. And then for x squared minus 4, I know that factors into x plus 2 times x minus 2. So I set those separately equal to 0, and I get x equals negative 2 and x equals 2. So remember, when it's just to the first power, that's an odd multiplicity. So we know this is kind of like, even though it's not multiplicity 1, because multiplicity means more than 1, we can just say it just to remind us. Those are both odd, which means it's going to cross at each of those. So it's going to cross at x equals negative 2, and it's going to cross at x equals 2. All right, so let's put these on here. So I've got x equals 2, x equals 0, and x equals negative 2. Let's spread those out, actually. All right, so 1, 2, 1, 2. Okay, so we've got an x-intercept at negative 2, at 0, and at 2. And we know it's going to bounce here. I'm just going to write a little b for bounce right there. Cross here and cross here. Okay, so the way you guys remember how I was referencing, are we coming from bottom or above? Well, the end behavior helps us know where to start. So our end behavior was in black. Now we're going to just follow the rules here. So I know it's going to approach this, and it's going to cross right there. It's got to cross at x equals negative 2. Then it's got to turn around and bounce back off that. And I know I got to turn back around because I got to cross at x equals 2. So I turn back around, cross, boom. That is the complete sketch of my function. And that is it. So what I'd like you to do is go ahead and on this next slide, there is the exit ticket. So I want you to complete this problem and then come back and come back into the classroom, or I will check it. So complete this exit ticket for me. Thanks, guys.